So we have a short instructional video kind of on probability models. The two we're going to focus on primarily, or at least I'm going to focus on primarily in this video, are tree diagrams and area models themselves. So there are a couple different probability models you can do. Those are the two that are going to be the main focus here. So when to create an area model, well, area implies multiplication, so we're going to keep that in mind here. Represents the entire sample space given that both spinners must be spun. Okay, so we're actually thinking about the probability of these events actually. So everything that could happen. So we could have made a systematic list. I'm not interested in doing that. I definitely easier to kind of lose something in that list. So I'm going to go ahead and create our area model here. Well, an area model typically has 2 dimensions. We've got a base and a height of this. So go ahead and just draw kind of a box for myself here. If it feels like something's a little too large, then we can go ahead and kind of trim it down a little bit. So I'm going to go ahead and identify these as spinner 1 and spinner 2. So let's go ahead and call this one spinner 1, and then I'll call this one spinner 2. So if I take spinner number 1 here across the top, I want to think about everything that could happen here. Well, if I take a look, it looks like I could get an A, a C, a D, or an E, or an F. All right, so I have basically 5 different things that could possibly happen. So I want to list those across the top here. So I went ahead and sectioned off the top with all of the different things that could happen. So A, C, D, E, and F. Now, what I want to do is I want to figure out, just by looking at the first spinner, the whole idea of sample space. So how many sections there are on the actual spinner. So if I go through and I count, looks like I'm going to get 1, 2, 3, 4, 5, 6, 7. There's 8 total spots. So my denominator for every single one of the things on spinner 1 is going to be 8. Then I'm going to take a look at, well, how many A's are there out of those 8? How many C's are there out of those 8? And that's going to give me the probability for landing on them. So if I take a look back up here, it looks like for A, there's only 1 of the 8 spots. So back at my table, the probability of landing on A specifically is going to be 1/8. And I'm going to go through and do the exact same thing for all the spots. So if I take a look at C, it looks like there's 1 out of the 8 spots total. So 1/8 for C. D has a couple of them. So 1, 2, 3, 4. And then you're welcome to simplify your fractions here, but you don't really need to. I'm actually a big fan of not simplifying, so I can see where the numerator and the denominator came from with regards to the spinner itself. Looks like E has 1/8, and then F has the remaining 1/8 as well. Now, if we did this correctly, another way to check this is you can take a look at all of those numbers across the top. All of those fractions have to add up to 1, as it represents 100% of the spinner itself. So if we add up all of those fractions, we do get 1. All right, I'm going to go through and do the exact same process with the second spinner, separate it out, and then figure out the probability of each one of those. So I set up my sections for spinner 2, and I go over to spinner 2. I'm going to find how many total slices I have here to represent the denominator. Looks like that's going to be 8 as well. And then I'll start finding the probability. So how many of those slices actually belong to those numbers? So with 1, looks like we've got a couple here. So it looks like 4 of them are going to belong to the 1. So the probability for 1 is going to be 4/8. Likewise, do the exact same thing with the remaining pieces. So 2, there's 2 sections of the 8, so that's going to be 2/8. And then if we take a look at the 3 has 1 section, as does the 4. So both the 3 and the 4 are going to have a 1/8 probability. Same rule applies. So if you take a look down, all of those probabilities, so the purple, those have to add up to 1. So they represent 100% of everything that could happen on spinner number 2. Now, since this is an area model, we're going to think about the probabilities occurring simultaneously. So I spin spinner 1 and then I spin spinner 2. The probability of both of the events occurring is going to be multiplication, since they are independent of each other. So whatever I spin on spinner number 1 isn't going to affect or have any type of an impact on what I spin on spin number 2. So from here, I'm just going to go ahead and multiply and fill them in. Remember that when you multiply fractions, you go straight across. So if I were to work on this very first box here, I know that I'm going to be multiplying the 1/8 and the 4/8. If I multiply straight across, that's going to give me a 4 times 1, which is 4, and an 8 times 8, which is 64. So if we go through, I'm just going to go through, and I'm not going to simplify my fractions for the exact same reason that I didn't simplify them in the first place. I think that it makes it just a little bit easier to see where the numbers are actually coming from, whereas if I simplify it might be a little confusing. So all we're going to do is just go ahead and fill in the rest of the boxes. So now that we have this completed, another thing to note, pretty important too, just like when we added across the top, we have to get 1. When we added down the side, we have to get 1. If you add all of those area model boxes together, you also have to get 1. So it represents 100% of the probability, or 100% of everything that could possibly happen. So we have our entire space now, which we should then be able to use to help answer some questions. Okay, let's take a look at the next one. So now we've got a tree diagram. Still kind of the same idea, it's just a different way to organize your data. So in a certain population, 60% are male and 40% are female. It is known that 8% and 3% of male and female, respectively, are colorblind. Okay, so the first bit of information that I know is the male-female portion. So that's going to be the first thing. And then we talk about colorblind with respect to male-female. So I want the colorblind to come second. So the first thing that we're going to do here is kind of build ourselves little branches. When we think about the 2 scenarios that could happen originally, or the information that's given to us, is we have male-female. Now the probability of male in this case is going to be 60%. I'm going to turn this into a decimal though, so that when I multiply to create my probabilities, or my entire sample space for the probabilities, I don't have to convert it later. We know we can't use percents when we're multiplying. Then we were told that either the population or the person within the population is either colorblind or not colorblind. So we're going to split this up here. So colorblind or not colorblind. We're going to fill in the information that was given to us. So we were told that 8% and 3% of male and female. Okay, so respectively means the 8% goes with male, the 3% goes with female. Okay, 8% is going to be 0.08, which means not colorblind is going to be 0.92. And do the exact same thing with the female down here at the bottom. So we've got colorblind and not colorblind. So colorblind and not colorblind. And we'll fill in that information as well. So colorblind for female, we were told was 3%. So this is going to be 0.03, which means that's going to be 0.97. Remember, in this identification, it's either colorblind or not colorblind. And just like the table before, those have to add up to 1 or 100%. Last thing we need to do is actually finish the model itself. Now, much like the area model, where what we do is we multiply the dimensions of the box, so the base and the height, in a tree diagram, we multiply down the branches. So if I want to multiply down this first branch, I would be multiplying the 0.60 that I had times the 0.08. If I multiply those together, I should get 0.048. And you can go down the boxes themselves, or down the branches. 0.6 and 0.92. That's going to give us 0.552. So we're just finishing down these branches so that we can complete our probability model, which is our tree diagram in this case. 0.012 and then 0.40 times 0.97, and that should give us 0.388. So now we have a completed probability model, and in this case, it's tree diagram.